I welcome Bhatia. It's really great to have him here for the webinar on the topic of revolution navigation, which is basically part of autonomous space navigation guidance. So I'll give you a brief about the speech. Dr. Rachit Bhatia is a PhD in aerospace engineering from Utah State University. He graduated in this and now currently working at SpaceNav, Colorado. His work includes designing, developing, and testing of different applications. He has experience or he has worked at rockets in Utah State University, and he's here with us to share the knowledge and his experiences in this. Very beneficial for the attendees and participants. And I'm very happy. I hope you guys will learn a lot from this webinar. One important thing to all the participants is the questions will be taken towards the end of the webinar. So by the time you have any queries, you can write them in the QA section and only in the QA section. Please don't write your questions in the chat section. And at the end, around for last 10 minutes, we'll be taking questions from each one of you. So I'll hand over the webinar to Dr. Rachit sir. Sir, please carry on.
Thank you, Dr. Jindal. Thank you for having me here. It's a pleasure. And as you have already told me, we have exactly 1 hour, so I'll be quick and make sure that I finish on time. Okay. So today, I will present on revolution in autonomous orbital navigation. And thank you for joining for the webinar. I will go over my background, state space representation, problem statement, and I would like to introduce 2 mathematical tools to you. If you're familiar with them, that would be great. Else I would like to make sure that you get a brief intro to observability analysis and linear coherence analysis. And finally, I will present my results, which I got for my research project, and then I will conclude. So I have a background in mechanical and aerospace engineering. I started with a bachelor's in mechanical engineering from SRM University. And then I finished my master's and PhD from Utah State University. I had internship regarding work experience. I had internship from Indian Institute of Astrophysics back in 2013. Then during my PhD, I worked as a research assistant, teaching assistant as well. So that was fun. And on campus, I was also active member of CubeSat team, rocket team. We get to do a lot of hand hardware projects and get some experience there. And now currently I'm working as an aerospace engineer at SpaceNav. I work on the space situational awareness topics, collision avoidance, simulations, risk assessment, etc. So that is the kind of projects that I handle. For those who are not much familiar about state space representation, because I used the representation in my mathematical model, I'll start with the basics so that everyone is on board. For a project like this, where we are analyzing and where we are simulating a given mathematical problem, we tend to use state space representation very often, and it comes very handy. It's a very powerful tool. It is a way to define the relationship between input and output and the state vector, where the state vector is the quantities that we are interested in. Say you want to estimate, or you want to know the position and velocity of a particular object, say a car or a rover, then you have inputs coming in from the dynamics, the kind of forces that are acting on the car, and output could be some kind of measurements that you are also taking, say, Doppler measurement, etc. So you can use that to measure X, that is a state vector. And there are different types of state space representation, linear time invariant, linear time variant, and those. So I'll leave those for you to read more about, but I'm just giving a brief intro here so that everyone is on board and have at least seen the equations. And the reason we deal with linear system more often is because they are easier to solve mathematically. So the solution for the given differential equation, we can get the differential equation solution for the X for the given initial condition, and we can also define the state transition matrix phi here. This phi or phi, sometimes some people call it phi, defines how the state changes from time t naught to time t. And this is a very powerful tool because now if you know position and velocity at time t naught, and you know it is time invariant system, and you have the dynamics, you have the initial condition, then you can get the state for other times as well. So it comes very handy. Now I will start with the problem statement, the procedure here. Just to give you background and some kind of motivation, the spacecraft navigation is a very critical component of any mission, of any space mission. And according to Decadal Survey, it is one of the 7 important challenges that kind of hold us back from exploring space. And the idea is we want to get to operate without real-time control from Earth and with limited data streams, which means if we are sending a spacecraft in space, we want to it to navigate itself rather than using deep space network or ground control to convey its position regularly and try to control where it goes. Because autonomous, making navigation autonomous will not only be a very critical component later in crewed missions, but also it frees up the communication lines which can be used for other scientific and scientific data to be conveyed. And it is very important as we go deeper into space. Further, it is important to define the motivation so that we can set our goals for the project and the objective very precisely. So I always recommend to be very clear on the motivation. The motivation for this project is to improve spacecraft's autonomy and versatility, to reduce complexity and cost, to enhance spaceflight safety. When I say enhance spaceflight safety, we mean that, say, if you are sending a crewed mission to Moon, then when the spacecraft is at on the other side of the Moon, which where it loses Earth connection to Earth, communication lines to Earth, then it would be so much better if they can navigate autonomously. It will make sure the crewed mission stays safe by having this redundant or extra precaution of capability to navigate autonomously. And it will also be beneficial in terms of resources, onboard resources. Similarly, it will also increase adaptability for varying space environment. So these are all the motivations that we want to address by working on a project like this, or while working on autonomous orbital navigation. I would also like to introduce you to gravity gradiometry. I'm not sure how many people are familiar with it. I was not when I started with this project. Gravity gradiometry is a very, it is not a very recent field. It has been there for quite a while. And the person you see on the slide is the Hungarian scientist Baron Roland Wortwoz, and he was the one who first invented a gravity gradiometer instrument. And it is a study. The way the gravity gradiometry is defined, it is the study and measurement of the gravity gradient. Now, what is gravity gradient? Gravity gradient is the derivative of the gravitational acceleration with respect to position. So basically, how gravity is changing as you change the position, or the gravitational acceleration, how it is changing as the position changes. And by measuring that, you can basically measure how non-spherical or spherical, they say obloid shape Earth has. We just tend to think that Earth is a perfect sphere. It is not. So it is very helpful and very important technique that has been used for quite a while in many applications for minerals exploration, to find where the mineral resources are, fossil fuels. It has been used in submarine navigation, but it has not been used for spacecraft navigation. So here what we are trying to push through is to see if we can use something like this to navigate autonomously in space. This is just the mathematical form where we have the second derivative of gravitational potential with respect to the position vector, and the tensor matrix is shown in its full form of 3 by 3, where we have, so this is a symmetric matrix and it has 0 trace, and it comes very handy when you're trying to estimate the components of this or the elements of this matrix. So this is just the mathematical form. So this was the mission. GOCHE mission was launched back in 2008, if I'm not wrong, by European Space Agency. And it used gravity gradiometer to measure Earth's gravitational field. And I could be wrong here, but up to very recently, it was, if not now, up to very recently, the measurement that GOCHE has got was the best resolution of gravitational field that data we have right now. And how did they do that? They use this accelerometer, 6 accelerometer configuration that has been shown on the right side. And these are electrostatic gravity gradiometer. When all these 6 accelerometers are configured together, they form an electrostatic gravity gradiometer. And look at the measurement noise resolution here, 10 to the power minus 12. That is amazing. So they use this to measure Earth's gravitational field. It is very costly, but that is the idea. This was 12 years ago. We are right now moving towards quantum sensors to do this kind of measurement. And if we can do that, if we can reduce the cost, if we can reduce the weight, then this application can be used for spacecraft navigation. And that is the idea. However, we cannot get this 350 million euro sensor. So what we did was to investigate this concept mathematically. The idea is GOCHE mission does gravitational mapping using these accelerometer measurements from the gravity gradiometer and the GPS navigation data. So they know where they are measuring this gravity gradient measurement, and they come up with the gravity map. Now the idea is, can we also, if we have the gravity gradient measurement on board and we have this map now, can we do autonomous orbital navigation? If we can, then we have solved the problem. So that is the entire concept that I'm going to put forward and present today. As I said, we are investigating this mathematically and doing a feasibility study. So what is the research objective? The research objective is to investigate the feasibility and sensor requirements. So as I've showed you that as I've shown you, we have this electrostatic gravity gradiometer, which has a measurement noise resolution of 10 power minus 12 meter per second square root hertz. And the idea is this much noise resolution sufficient to do autonomous orbit determination, or we need better sensors? If yes, how much better do we need? And what orbital configurations can we do? Can we just do LEO? Can we do GEO as well, higher altitudes? So here today I will only present LEO results, but we have investigated in our other research papers about GEO as well. And even I've done some simulations for lunar orbit as well. So this is a very promising concept. And I would like to present those results later on. But before that, I'd like to set up the problem here. Now, when we have such a problem statement, we tend to go towards mathematical models. We model what we know, and then see if we can estimate our desired state vector in turn. So we have two. Generally, we have two models. One is dynamical model, which encapsulates the entire forces that are causing the motion or that is acting on the system. And then we have measurement model, which defines the measurement information that is coming in so that we can estimate the quantities of interest. So I'm just giving you an overview of the problem here so that you can get a better understanding of what we are dealing here and how we are setting up the problem. So having defined that, now we define the state vector, because we want to know what are the quantities of interest we want to estimate. And the state vector here, defined by x or denoted by x, has subparts as spacecraft states, environmental parameter states, and accelerometer parameter states. And spacecraft states include position, velocity, quaternion, which is just the attitude, what is the orientation of the spacecraft, angular velocity, and the position of the center of mass of the spacecraft. We want to know that as well, because turns out I'm not sure if I will be presenting entire mathematical equations, because I don't want to intimidate you. But center of mass position is a very important quantity and has a significant impact on how we set up the problem. So that is why it is a quantity of interest. We also want to know environmental parameters here: ballistic coefficient, reference atmospheric density, scale height, and then definitely accelerometer states, because we want to investigate the feasibility of sensors, sensor requirements. So we have position of accelerometer, bias, scale factor, misalignment. So now you can see this is such a big state vector. And that is one problem that we faced. And that is why we tried to solve this using linear covariance rather than Monte Carlo, because we have such a big state vector. Fortunately, we can linearize the system, and we can use linear covariance tool, and that came very handy. So I will go over that as well. First of all, nonlinear modeling is done as I've already said, that we define the mathematical models. So we have the mathematical model in its pure form, nonlinear model, the dynamics we have, and we show the relationship between the dynamics as a function of state and time, and then we add process noise here, and then similarly we have measurements, which is shown as a function of state, and we add measurement noise. And here is a very crude diagram of how the accelerometers are set up in this configuration. So we have accelerometer 1, accelerometer 4. This is center of mass, and these are different position vectors. I will go over the procedure that I follow. The procedure is very simple: linearize the nonlinear models about reference state vector. Reference state will include the nominal trajectory here, LEO orbit that we are going to simulate. Then we derive linearized equations of motion and measurement partials, which I'll be discussing. If you don't know about them, don't worry. And then I will also introduce you to observability analysis, and we will check before running the full simulation. We'll first check if the measurements that we are planning or the measurement model that we are formulating into the system, is it sufficient to estimate the states of interest, or do we need more measurements? So, and we will see it becomes very important. Then we finally formulate this linear covariance tool with linearized dynamics and simulate and conduct error budget analysis. So I just wanted to give you an overview of where we are heading towards. Okay, linearized model. So we have seen nonlinear equations, and I've tried my best to reduce the equations to the least. So these are the simplest equations here. So and this is very simple. We have seen the nonlinear equation. Now what we are doing is we are taking the partial of that function f, which was a nonlinear function of state and time. We are taking a partial with respect to the state vector and evaluating it at nominal trajectory. And similarly, we do it for the measurement nonlinear function, and we get the measurement partial. So this is called Jacobian, or equation of motion, or state dynamic, and then this is called measurement partial. And G is just the mapping of process noise onto the dynamics, and measurement noise is also added to the linearized measurements. And here, if you're not familiar, process noise is added because we cannot model everything, right? We can model the dynamics up to the best knowledge, but there will still be some kind of noise in there, some kind of unknowns. So process noise take care of that. And measurement noise is if you have used accelerometer on your mobile phone, if you have used any sensor, every sensor has some kind of measurement noise. So that is modeled here mathematically. I hope that makes sense. Okay, observability analysis. This is a very powerful tool because, as I said, it is used to see if the system is observable, which basically means I can read this entire paragraph. This is the mathematical definition of observability, but I won't. You can go ahead and read. I will just give you the crude form here. What we are trying to see is if we want to estimate the state vector x, and we have input u and output y at given time, then can we uniquely estimate the state x if we or basically if we have this if you have the measurements over here, accelerometer measurements coming in, then are those accelerometer measurements sufficient enough to estimate position and velocity or not? And that is what we check with observability analysis. This is the mathematical equation. OK is called observability Gramian. Phi, I've already told you, is state transition matrix. H is measurement partial. So I've introduced you, there was a reason I introduced you to these concepts, because using these quantities, we can now formulate and get observability Gramian for the given measurement. And if this observability Gramian is full rank, and I hope you remember full rank, what does full rank mean? We have studied it in matrix chapter back in 9th or 10th standard. So if it is full rank, then we know that the measurements that we have are sufficient to get the state that we are trying to estimate. Okay, these are the results. So initially, I simulated this for a very simple scenario where we have a low Earth orbit, and these are the orbital elements: inclination, eccentricity, how we define an orbit. Okay, and we are getting measurement, these accelerometer measurements every 30 seconds for 1500 seconds. So 1500 seconds is the total time. And we see that for circular orbit, we have rank 6. So 3 components of position, 3 components of velocity, and we have rank 6. So that means it is observable. So we see similarly for elliptical and this point mass 4x4, 8x8 are different gravitational model. So when I say point mass, that means the Earth is perfectly spherical. So even when the Earth is perfectly spherical, we can still, theoretically, we can still estimate position and velocity. So that was the whole entire idea of this simulation uh, when we did observability analysis. Next, we thought, okay, we can get position and velocity. Can we also get attitude or the orientation? Another 3 components. And turns out we cannot get it for one case, we can get it for other scenarios. And however, the condition number is very large. As you can see, previously it was just 110, 106. Now it is in 10 by 12, 10 by 8 magnitude. The condition number is another property of a matrix, and if it is large, then that means the matrix is becoming unstable. And even though theoretically we can, it seems like we can get the attitude as well, but it will create problem. So we decided to add a star camera just to get the orientation, but we can still get position and velocity. And so those were the so before running complete simulation, we did this observability analysis and we got some important information to make sure that we add star camera measurements to our entire simulation so that we can estimate not just position and velocity, we can also estimate attitude. And that way we can get entire state vector of the spacecraft, and we can do the autonomous orbital navigation, basically. So having concluded with these results, we will now go ahead and set up the linear covariance analysis tool. So linear covariance analysis tool is a very powerful tool, and the way it is used is, I'm not sure if you're familiar with Monte Carlo analysis, but Monte Carlo analysis basically needs, you need to run it a number of times to get to know what is how a particular parameter, how the variation in a particular parameter is affecting the state, the quantities of interest. For example, if you are launching a rocket and you know that there will be some wind, high altitude winds. Now you can measure high altitude winds, but there will be some uncertainty in there. Now, you know the uncertainty as well. You know that there will be this much uncertainty in wind, high altitude wind speeds, etc. But you do not know if that much variation is sufficient for you to have a good launch or not. So you can run a Monte Carlo analysis over that variation, or you can do linear covariance analysis. So these tools are used to see how the variation in particular parameters affect the entire system. And to do this setup, to run this mathematical tool, we segment the problem into 2 models: truth and filter. Truth model is a mathematical representation of the real dynamics to the best of our knowledge. It includes complete environmental model, all the states necessary to define the system dynamics. While the filter model is the representation of the dynamical and measurement model that will be processed on board the flight, which means what the sensors will experience or what we think the sensors will experience. And using these two models, we can propagate and update them over time. We can basically run them over a certain period of time. We can see how they emerge, and then we can, using these quantities at different epochs, say final time, we can get the error between uh, these two truth and filter states to 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 know the performance of the entire setup, and that helps us how much variation is is uh, is uh, is causing how much error in the final states or the state at particular epoch. Okay, so some as I said, linear coherence analysis, we have filter and truth. So we set up the filter model here, and you should not be intimidated by these equations. These are just the covariance. When I say covariance, covariance is basically how much uncertainty we have on filter state vector, and we have state transition matrix here. So equation 1 is called Riccati equation, and we are basically propagating the filter covariance over time and adding process noise covariance to it. And then we update it as well using the measurement at time tk. And excuse me. And this is here k hat is called Kalman gain, which is very famous Kalman filter, of course. And we update this covariance as we get the measurement. So what basically is happening, if you just want to know the crude form, is we are saying we have certain uncertainty on the state vector. Say we know position and velocity up to certain with certain error, say position plus and minus 5 meter, and velocity plus and minus 0.1 meter per second. I'm just giving you an example here. What we will do is we will put this into a matrix form, and we will use state transition matrix to run it over time, and we will see how the covariance change, how the uncertainty change. And during that time, we will also get some measurements from, remember, we have accelerometer and different sensors on board. So we'll get the measurements and we'll use them to see if we can improve our uncertainty, if we can reduce it, or does it still grow. So that is what is happening here. We also set up augmented covariance. And augmented covariance is basically a similar form as filter covariance, but it also include truth covariance. So what we do, we have set up the filter covariance, and now we are also setting up the truth and the filter. We are setting them in the same matrix and putting them in augmented covariance form. And the similar thing happening here, we propagate it and then we update it. In the end, what we use is we use the true navigation error, which is basically we are subtracting the final uncertainty value of the truth covariance and the filter covariance to see how much error we have on position, velocity, and orientation. And for this simulation, I do it for 5 orbits, and I get it in local vertical, local horizontal frame because it is just easier to read and understand. And we do it for all the state vectors, and that will help us know how certain parameters are affecting the final state vector. So these are the performance metrics. Now, what type of parameters I'm evaluating? I'm evaluating the initial uncertainty. For example, as I said, initial uncertainty on spacecraft position and velocity. We start in the orbit and we see we do not know if we are 1 kilometer uh, uh, we are 1 kilometer to the radial error. Is there 1 kilometer error in radial or in track or cross track? So there are these different components, and similarly some error on velocity. So what we are trying to do is we have some initial uncertainty on spacecraft position, velocity, attitude, center of mass position. Then we have translational process noise, rotational process noise. We have uncertainty on atmospheric models, ballistic coefficient, etc. Similarly, we have uncertainty on accelerometer parameters like the accelerometer position, etc., accelerometer bias, accelerometer scale factor, and we also have star camera measurement noise. So we have all these different error groups that we combine, and using linear covariance tool, we can know if we have 1 kilometer initial uncertainty on spacecraft position, is how much will that itself cause a final error in the position. And that is very important because it turns out if we can reduce that initial uncertainty, then we can improve our final solution. And similarly, if we can improve our knowledge about accelerometer position, where accelerometer is on the spacecraft exactly, then we can improve our final navigation solution. So that is the entire thing that we are doing here. Okay, so now I will just set up the simulation and present the results for you. I hope it will make sense. So we have following spacecraft parameters. We have a spherical spacecraft, and not too big, just 0.3 meters of radius. And we have certain ballistic number, reference atmospheric density. So these are just the parameters that I've used. And then we have the time constants here, because I won't go into this detail because it will be a time-taking thing. But time constant is basically how ballistic coefficient is changing. The dynamics of the ballistic coefficient is changing while the spacecraft is in orbit. And over here, I use first order Markov process. The interesting thing here is that you would like to see is the initial uncertainty is 500 meters on spacecraft position in radial direction and 1,000 meter in along track and cross track, and similarly other initial uncertainties. Then we set up different cost models for our, because there are so many parameters, it would be hard if I'm changing everything. So what I'd say is we have high cost model where we have everything to the best. We have very high resolution gravity model. We have a very good knowledge of reference atmospheric density, and we know center of mass position very well, so on. Moderate cost, they are a magnitude or two off. And then low cost is not a good model. We basically have very poor knowledge. And the reason I do this is because, as I told you, that we are heading towards these other advanced accelerometers, which are cold atom and using quantum physics. And they have very high noise resolution. So using that, we will be able to see if noise resolution of 10 power minus 13 is sufficient, 10 power minus 11 is sufficient, or 10 power minus 10 is sufficient. And that is the entire purpose of this, this research. Because what we are trying to do is we are trying to check if the current sensors and sensor requirements that we have, current sensors, are sufficient for spacecraft navigation or not. If not, how much better do we need? And that is why we are setting up this entire simulation. Okay, I also present the orbital parameters of different orbits that I do, LEO orbit, low Earth orbit, and polar sun-sync orbit. I don't think I'm presenting polar results today, but This LEO orbit is basically a very circular, near circular orbit, and these are the orbital parameters. I'm simulating it for 5 orbits. Simulation results. Okay, so I do it for 2 cases, rotating and non-rotating spacecraft, because that is important, as if we have a non-rotating spacecraft, then we want to see how much will that affect the navigation solution. We want our concept to be valid in a number of different scenarios. So can we navigate better only when the spacecraft is not rotating, or can we navigate better even when the spacecraft is rotating? So we evaluate those 2 cases. So this first result is for a non-rotating spacecraft, and we have 3 accelerometers, 1 star camera on board. The baseline is basically the distance between 2 accelerometers, so that is 0.5 meters. And when I say large time constant, basically these parameters, atmospheric parameters, are not changing. Now, how should you interpret this result? The way you should interpret this result is we are seeing that the total error is decreases. Remember, a long track was 1,000 meter or 1 kilometer. It decreases over time, orbit number. It decreases to hundreds of meters. And out of this total, accelerometer position is contributing to the max. So we get to know that if we can improve our knowledge of accelerometer position, where the accelerometer is on the spacecraft, then we can get a much better solution here. Similarly, for radial, we see that instead of accelerometer position, the star camera noise is a major factor. So I hope you're getting an idea how powerful these results are, because now we can know what do we need to improve so as to improve our final navigation solution. So if you want, instead of hundreds of meters, if you want tens of meter uncertainty, if that is what you want, then you should improve your accelerometer position uncertainty. And that is the entire idea. Similarly, for orientation, we see that star camera noise is the major contributor. And I tabulate the results here just to give you an idea, and these are final time results. And we see that the final total error on spacecraft position is 105.36 meters. So we are getting good estimate. And similarly, attitude is being estimated to micro, actually, 10⁻⁵ radians. That is amazing. So we can see that the concept is working. We can see what are the major error sources. Error source 1 is the major contributor. Error source 2 is the second most major contributor, and so on. And how will that change now for rotating? So this is for non-rotating, and for rotating, we will see that instead of 105.36, 103.33. So it turns out, if you have a rotating spacecraft, it helps navigate using this concept, at least theoretically, or what we are the model that we are using. So so this is interesting. Similarly, what happens if we increase the number of accelerometers? So now we have 6 accelerometers. Then we can improve our results much more. From hundreds of meters, we are now down to 73 meters and 81 meters. And now if we increase the baseline, if we just, instead of having more accelerometers, if we just separate the accelerometers instead of 0.5 meter by 1 meter, so we are increasing the length of the spacecraft, then we can get similar performance. And this is, again, you do not need more accelerometers, you just need a bigger spacecraft. So that can be very helpful. And at the same time, we can also see what are the major sources of error. So if we can get a better star camera, we can reduce the noise on star camera, then we can get better results. Similarly, if we have both 6 accelerometers and 1 meter baseline, then just 50s of meters. So overall, the summary is that high cost system gives a good performance. So we right now have the sensors that we used on Goche was 10 per minus 12 meter per second square root hertz resolution. If we can use 10 per minus 13, then we can actually navigate autonomously in space. That is the conclusion of this research. We also see how the baseline length and number of accelerometers change the final results. So in conclusion, I will say that ultra precision accelerometers are needed. So we need much more research in the hardware of these sensors, and we need to improve upon sensor requirements in terms of sensor noise and using physics and using these sensor instrumentation knowledge. And theoretically, it is possible to use this concept to autonomously navigate in space. And the best thing about this is that instead of using a camera or image tracking or feature tracking, as it is mostly popularly known, if you use this concept, this is universal. Gravity is everywhere. And if you can get a good gravity model, then we can navigate autonomously around Moon, around Mars, and so on. So this is a very powerful concept and much more generic. As I said, I also checked for polar LEO orbit, and it performs better than LEO. So just changing the inclination of the orbit also helps. Accelerometer error are the major source of error, so we need to improve both accelerometer and star camera parameters. The unique contribution of this research has been that we validated that such a concept can be used for autonomous space navigation. And we are already seeing the development of these sensors, and if we can use it for such an application, that will only make the space exploration much less complex. It will always be complex, but it will help improve our current system and go further in space and explore more. We also used linear coherence analysis for this problem. This was the first time as per literature survey, and we conducted this error budget analysis as I presented. Future work, we would like to do this for quantum sensors that are coming up, and we would like to include more uncertainties and use better model, and also do for different orbital regimes. I've published related to on this research, and these are my publications and these are my references. So I hope you at least you got to know about these mathematical tools which you can use in your research, and this was helpful to get some acquaintance about this concept that we are researching and we are proposing. Thank you for your attention. I would be very happy to take any questions you have.
Yes, sir. Thank you so much for the webinar. So we have questions. So let's first. polar Leo.
I'm sorry, I'm losing you. There's your voice is not clear. Can you repeat?
Yeah.
Yes.
The question is, explain more about polar LEO navigation.
Okay, so polar LEO navigation is not a different navigation. Polar LEO is just a different orbit. We have different orbits, or as we say, we have classified orbits around Earth differently. We have low Earth orbit, which is basically any orbit which is up to the altitude of 1,000 to 2,000 kilometers. Uh, it's not very. It depends on the definition, but basically anything below 2,000 is mostly classified as low Earth orbit. Then we have geo orbit, which is very popular, which where we send most of our communications and image um, and TV satellites up there, and those are up at altitude of around 35,000 kilometer, and so those are high altitude orbits. Now, polar is basically anything with inclination above 90 degrees. So we have inclination. So I would suggest read more about the orbital mechanics here. But we define an orbit of a spacecraft around Earth. We define it with different different parameters. We have altitude. We have how circular it is. So eccentricity. Then we have what is the inclination, how is it inclined around the Earth. Then what point it goes up, that's called ascending node. uh, I'm basically giving you a very vague definition here, but these are different parameters that we use to define where the spacecraft is in an orbit around Earth. And when I say polar Leo is any orbit with an inclination above 90 degree, and Leo means low Earth altitude, low Earth orbit. So what I did was use the same setup for an orbit which is uh, around 500, 600 kilometer circular orbit, and with a decent inclination of 50 degrees, which is around what the ISS, International Space Station, is. And then I just change the orbit inclination to 90 degrees and see how will that affect. So the reason the inclination will make a difference is because now it will be flying over different parts of Earth. And as you know, the Earth's gravity is different around polar region than around equatorial region. So just changing the inclination will affect the overall performance here. And that was the purpose of changing the inclination and see how will that affect, and we get to see that it performs better.
Okay, sir. So the next question is, how do you make sure that your linearized model is a good representation of actual nonlinear dynamics?
That is a very good question. Yes, and that is very important. And the reason we can say that our model is uh, is reasonably linearized and is reasonably a good representative of the nonlinear model is because of the dynamics that we are dealing here with. The dynamics do not change in an instant. The dynamics are uh, take basically orbital dynamics are uh, are can be linearized. And the reason I say that, for example, if you're in an orbit in around Earth, and you are dealing with nonlinear dynamics, but now if we linearize it such that you always stay near that nominal orbit, then it is very reasonable because nothing very instantaneous is happening, or very instantaneous force is being applied to your system, which will make the system instantaneously non-linear. And because we can approximate the nominal or the reference trajectory reasonably well, because we are assuming that we are staying near that reference orbit, and uh, because of optical mechanics that is possible, we can say here that the linearized dynamics are a good representative. However, uh, this is the best explanation right now, but there are tools for other problems, for other systems where you are dealing with uh, nonlinear dynamics and you are not as much sure about or certain about the representation of the linearized dynamics. Then you will have to do Monte Carlo analysis. Um, for this problem, as I've said, the state vector is so big that Monte Carlo analysis will be an entirely different project. But that is where you use Monte Carlo analysis if you get the same result or similar results from Monte Carlo as well, then you have basically validated that your linearized dynamics or linearized model is a good representative. I hope that gives you that explains your question.
Yes, sir. So the next question is, do we use Newtonian physics for gravitational model or the general?
Now here Newtonian is sufficient. Um, you do not need a general relativity here, but you can definitely use that as well. Uh, those are different levels. For this setup, Newtonian is sufficient to give you the kind of results that we are we are trying to get, and because here we are just dealing with something reasonably at speeds less than the speed of light. So Newtonian is definitely a good system.
Okay, sir. One last question we'll take here is, when we increase the number of accelerometers, look, how do we embed their information?
I'm sorry, I'm losing you. You may have to repeat the question. I'm sorry. Hello.
When we increase hello, can you hear me? Hello, hello.
Yes. Yes. There's. I might be losing you at certain points, but yeah. Uh, can you just repeat the question?
Yes, yes,
Doc-
yes.
Dr. General, please
When
close your mic.
Hello.
hello.
Yes.
Yes, accelerometers located at different positions on our spacecraft. How do we embed their position information in our measurement model?
Yes. Um, I have not presented the entire measurement model here. Uh, that would have taken another hour of presentation. But it is not very difficult. Uh, if you remember the diagram, the figure I showed you, uh, the dynamics can be made are a function of those position vector where and we define the position vector of the accelerometer with respect to the center of the spacecraft, and we also define the center of mass of the spacecraft with respect to the center of the spacecraft, and using those position vectors we can finally define both dynamics and measurements. And yeah, it is not a very difficult thing. I think that is all I would like to say. I can forward you my dissertation on this, and there's the complete measurement model in there, and it is not very difficult. It is very easy. We just make it a function, make the dynamics and measurements a function of the position of accelerometer.
Okay, sir. Thank you so much. Thank you so much to all the participants. And also, I would like to take this opportunity to thank our Chancellor, Vice Chancellor, and all the people who are there who have been continuously motivating us for organizing such useful webinars for the people who are there who have attended. And I hope they have learned so many new things with this webinar, and it will be very beneficial to them for their future correspondence or future work that they will be thinking.
Definitely. Thank you, Dr. General, for having me.
IT, this thing. Thank you so much. Thank you so much.
Thank you. Thank you.